Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a pre-calculus lecture. I hope you enjoy it. This is section 5.2, which is on verifying trigonometric identities. All right, and the idea here with verifying identities is that we want to use a whole bunch of the identities that we learned in 5.1 or prior to that in order to verify that an equation is in fact true. And let's start simple. Let's say that I start with something like sine squared theta plus cosine squared theta over cosine squared theta times secant squared theta, and we want to show that this is in fact equal to just 1. All right. Now the idea here is that we want to start with one side of the equation and then end up at the other, and always start with the side that has more stuff to do. All right, the side that looks more complicated. So in this case, I'm going to start at the left hand side because this fraction has a lot more stuff going on than just this number 1. So I'm starting with sine squared theta plus cosine squared theta over cosine squared theta times secant squared theta. And well, here we know that from the Pythagorean identities that sine squared plus cosine squared is simply equal to 1. So the numerator is just 1. From the bottom, I've got cosine squared times secant squared is, well, secant is a reciprocal of cosine, so I end up with 1 over cosine squared. And at that point, we simply see that these two reduce, giving us just 1 over 1, which is simply 1, which is the right-hand side. And now we're done. All right, so we started with one side, we applied some identities in the middle, and we ended up at the other side. All right, that's how you want to verify these trig identities. Start at one side and go and end up somehow at the other side. You do not want to start moving things from one side to the other. All right. Notice that at no point, there we go. Notice that at no point did I actually move this that was down here up there. Algebraically, it is fine because we have an equation, but the idea is that we don't know that this equation actually is true. We want to show that it is true by starting at one end and ending at the other. All right. So let's do another one. Let's say that I had something like 2 cosecant squared theta is equal to 1 over 1 minus cosine theta plus 1 over 1 plus cosine theta. All right. Now, again, you want to start with the side that it looks like it has more stuff going on. As written, the right-hand side here, to me, looks like it has more stuff going on for you. In other words, there's more algebra, more arithmetic that I can apply to this side than there is on this side. So I'm going to start with the right-hand side. And I have 1 over 1 minus cosine theta plus 1 over 1 plus cosine theta. And since I see here that these are two fractions, I'm going to combine them. So I have 1 minus cosine theta times 1 plus cosine theta. And since I'm adding these fractions, this is going to give me 1 plus cosine theta plus 1 minus cosine theta, right? Essentially, I just multiply those to the numerators. Now, at that point, the parentheses on the numerator are not really doing anything. So I have 1 plus 1, that's 2. Cosine plus negative cosine cancels out. On the bottom, I've got the product of conjugates, so I end up with the difference of squares. Now, 1 minus cosine squared from the Pythagorean identities, and by the way, the one I'm talking about is that sine squared plus cosine squared is equal to 1, which tells me that sine squared is equal to 1 minus cosine squared. So I can use that to rewrite this as 2 over sine squared theta. But in here, having sine squared on the bottom is the same as having cosecant on top, which is our left-hand side. So now we're done verifying it. And again, Notice that at no point did I move one stuff from one side to the other of the equation. I just started on one side of the equation, did a whole bunch of stuff, and made sure that it simplified to the other side. All right. Let's do another one. Let's say, so that was B. Let's say that I had something like cosine x times cotangent x is equal to cosecant x minus sine x. All right. And again, the idea is that we want to start with the side that looks like it has more stuff going on. Now, as written, it doesn't seem like there's a side that has more stuff going on right away. But I will say that this has a lot of extra hidden stuff. How come? Because I can rewrite this side as 1 over sine x minus sine x. And look at that. Suddenly we have a whole bunch of arithmetic we can apply here because of fractions. So that's what I'm going to do. I'm going to start with that side. I'm going to start with the right-hand side here. So starting with the right-hand side, we've got cosecant x, and that's not how you abbreviate cosecant x minus sine x, and we just said that this can be rewritten as 1 over sine minus sine. And then if I come up with a common denominator, the common denominator would simply be sine. The first one stays as 1. This sine becomes sine squared. And then what can we do after that? Well, 1 minus sine squared is really cosine squared. And we have that over sine. And remember, 1 minus sine squared is cosine squared by a similar process to this one over here. And finally here, I can rewrite this as cosine x times cosine x, all of that over sine x. And if I choose to pair this cosine and this sine together, what I end up with here really is cosine x times cotangent x, which was the left-hand side. So we verified that that is a true identity. All right. And they can get more complicated than this. So for example, see D. Let's say that we had something like cosecant x plus cotangent x be equal to sine x over 1 minus cosine x. All right. And as far as choosing which side to start with, well, both of these have a lot going for them as far as which one to start with. All right. And in fact, I'm going to do this twice. First, choosing the left-hand side to start with. All right. So starting with the left-hand side, cosecant. Well, let me just go ahead and rewrite it. So I have cosecant x plus cotangent x. Well, cosecant is 1 over sine. Cotangent is cosine over sine, which gives me that I have 1 plus cosine x over sine x. Right, because I have a common denominator, so I can just go ahead and rewrite it that way. But at this point, well, what do? That's not what I wanted. I want sine on top and 1 minus cosine on bottom. Well, what we can do here is essentially we can force to end up with this. How? Well, I see that we want sine on top. I see that we want 1 minus cosine on bottom. So I'm going to choose one of those two to multiply by 1. All right. And it doesn't really matter which of the two you choose. All right. In this case, I'm going to choose sine over sine. And again, it doesn't matter which one you choose from these two. It would end up with the same answer somehow, or an equivalent answer. Now, if I multiply by sine over sine, what does that give me? That gives me 1 plus cosine x times sine x over sine times sine is sine square x. All right. Now, from the Pythagorean identities, sine squared can be rewritten as 1 minus cosine squared. So I really have here 1 plus cosine of x times sine x over 1 minus cosine squared. And then the denominator, 1 minus cosine squared, is a difference of squares. So I can in fact factor that, because that would factor to be 1 plus cosine times 1 minus sine. Right? Because the difference of squares becomes a product of conjugates. At that point, we see that 1 plus cosines cancel out, leaving me with my final answer of sine x over 1 minus, that should have said cosine right there. Let's rewrite that. Because we were factoring 1 minus cosine. There we go. So sine x over 1 minus cosine x, which was in fact our right-hand side. Sine over 1 minus cosine. Right? Now, I said I was going to do this in two ways. So let's go ahead and redo this problem, but starting on the right-hand side. So we'll do this one in blue, and we'll call it d star. So we're going to start on the right-hand side, meaning that we're going to start with sine x over 1 minus cosine x. All right. And we're going to start by multiplying by 1. All right. And again, the 1 can be either the numerator itself or the denominator, or the conjugate of the denominator. I'm going to use the conjugate of the denominator. All right. The reason I'm doing this is so that I end up with, in the numerator, I end up with sine of x times 1 plus cosine of x. And at the bottom, I've got the product of conjugates. It's the difference of squares. So I end up with 1 minus cosine squared of x. However, 1 minus cosine squared is simply sine squared. And since we have a sine x on top, we're going to be able to reduce that, giving me here just simply 1 plus cosine x over sine x. Right, this sine and this sine squared, they reduce to just have a sine on the bottom. And this I can rewrite as 1 minus sine x plus cosine x over sine x, which, if you'll note, is 1 over sine is cosecant, cosine over sine is cotangent. So I end up with what we wanted, cosecant plus cotangent. And that would be our left-hand side. And now we're done. All right. So again, the point here is that you can start with whichever side you want. The point is that we want to be able to manipulate it to end up with the other side somehow. Let's do another one. So that was D. E. Let's say that I had something like 1 minus cosine theta over cosine theta is equal to tan squared theta over 1 plus secant theta. All right, and again, what you want to do is see which side has more stuff going on for it, and start with that. All right, now in here, the very first thing I see is that this side, the right-hand side, it's got more stuff going on for it than the left side. All right, so I'm going to start with that. It's possible to start with the left one, but I'm going to start with the right-hand side in this case. So if I start with the right-hand side, well, what do I have? I have tan squared over 1 plus secant theta. I'm going to multiply this by 1. And the one that I'm going to multiply by is going to be the conjugate of the denominator, 1 minus secant theta over 1 minus secant theta. The reason for that is, well, now I end up with tan squared theta times 1 minus secant theta. On the bottom, I've got the product of conjugates. That's the difference of squares. All right. But now that I've got that, let's rewrite this because this looks similar to something that we need. And we got tan squared theta on top, 1 minus secant theta. And then this, I'm going to write it as the negative of secant squared theta minus 1. Now, why do I want that? Well, the thing is that I know that 1 plus tan squared theta is equal to secant squared theta, meaning that tan squared theta is equal to secant squared theta minus 1. So in here, when I saw 1 minus secant squared, I said, hey, that kind of looks like something from the Pythagorean identities. However, it's in the wrong order, which is why I factored out that negative. All right. And at that point, I'm going to say, well, secant squared theta minus 1, that's tan squared. So I can say here that this is just simply, well, the top stays the same, but the bottom is going to be negative tan squared theta, which means here that, well, the tan squares cancel each other out, so I end up with just the negative of 1 minus secant theta. In other words, secant theta minus 1. But secant is 1 over cosine, so I have 1 over cosine minus 1. But if I come up with a common denominator, this 1 was already over cosine, so it stays the same. This 1, it was originally over 1. To go from 1 to cosine, multiply by cosine, so I need to multiply by cosine. And look at that. That is the left-hand side. 1 minus cosine over cosine. So that is the left-hand side. And now we're done. We verified that identity. All right. Let's do another one. So that was E. F. So we can have something like tan cube of x being equal to tan x times secant squared of x minus tan x. All right. And this might seem complicated as to how to start it, but it's actually relatively simple. All right. And I'm going to start with the right-hand side only because I see more stuff to do. I've got 2 tangents there that I can factor out. So if I start with the right-hand side, I'm going to say, well, I've got tan x times secant square x minus tan x. And I can factor out a tan x, leaving me with a secant squared minus 1. But I know what secant squared minus 1 is. We just solve for that. Secant squared minus 1 was tan squared. So what I'm going to say is that this becomes tan x times tan squared of x. And tangent times tangent squared is tan cubed, which is our left-hand side. And now we're done. All right. Let's do another one. G. Let's say that I had something like sine cubed times cosine to the 4th is equal to cosine to the 4th minus cosine to the 6th, all of that times sine. All right. So here we go. Again, this might look a lot more complicated than it really is. I'm going to start with the left-hand side because I see that I can factor out some cosines out of here. So if I start, the right-hand side. So I start with the right-hand side, and I've got cosine to the 4th minus cosine to the 6th, and all of that times sine. From these first two, I'm going to take out a cosine to the 4th. What am I left with? Well, I'm left with 1 minus cosine squared. But then we know that 1 minus cosine squared, that's really sine squared. So I really have here cosine to the 4th times sine squared, and then that times sine. But then I've got sine squared times sine, that's sine cubed. And we have that multiplied by cosine to the 4th, which is our left-hand side. And now we're done. All right, so again, the idea is to start from one side, end up at the other. Let's do maybe a couple of more. So that was G. H. Let's say that I had something like cosine theta minus cosine theta over 1 minus tan theta is equal to sine theta times cosine theta over sine theta minus cosine theta. All right. Now, in here, the very first thing that I'm going to recommend that you do is, well, choose the side that has more stuff going on for it, right? Now, between choosing these two, it might be difficult to decide which one has more stuff going on for it. In other words, which one you can manipulate more. But I would say that the left-hand side is probably the one that you can manipulate more because we have multiple fractions, right? Cosine over 1, that's a fraction. We have fractions being added. Over here is just one simple statement of one fraction. So I'm going to work with the left-hand side and see where that leads us. So I start with the left-hand side, and I've got cosine theta minus cosine theta over 1 minus tan theta. All right. Now, what can we do here? Well, the very first thing that I'm going to do here is I'm going to rewrite that tangent. All right. Actually, before that, I'm going to come up with a common denominator. The common denominator being 1 minus tangent. And since this cosine is originally over 1, I'm going to start by taking cosine theta and multiplying it by 1 minus tan theta, and we still have this minus cosine theta. Now, at that point, distribute the cosine theta, so I end up with cosine theta minus cosine theta tan theta, and then that minus cosine theta over 1 minus tan theta, right? At that point, I see that cosine theta minus cosine theta cancel each other out. What else do I see? Well, I see that I'm still working with tangent, so I'm going to rewrite tangent as sine over cosine. So on the top, I've got negative cosine theta times sine theta over cosine theta, and on the bottom, I've got 1 minus sine theta over cosine theta. If I multiply this entire statement, because I've got fractions all over the place, if I multiply this entire statement by cosine theta over cosine theta, you would see that on the numerator, this cosine and this cosine cancel each other out. So you end up simply with negative cosine theta times sine theta. On the bottom, distribute this cosine. Cosine times 1 is cosine, and cosine times sine over cosine is just sine. But that's not exactly what we wanted, is it? We wanted a positive sine times cosine over sine minus cosine. Well, we're almost there. Just bring this negative down to the bottom. In other words, you can rewrite this as sine theta times cosine theta over the negative of cosine theta minus sine theta, giving us our desired result of sine theta times cosine theta over sine theta minus cosine theta. And that would be our right-hand side, exactly as written. So that's our right-hand side, and now we're done. All right. And this can get even more complicated, all right? So for example, so we were at H, so I. We can have something like cosine of sine inverse being equal to the square root of 1 minus x squared. All right. Now, let's see how we can verify this one. Well, the very first thing I'm going to do here is I'm going to build a triangle implied by the problem. In here, I'm going to say this right here is theta. All right. And remember that sine theta only exists in quadrants 1 and 4. Right? Excuse me, sine inverse. The range of sine inverse is only in quadrants 1 or 4. So that must mean that I am working with either this triangle or this triangle. Let's do the top one first. And you'll see that either way we're going to get the same result. All right. So if I am working with this triangle here, and theta is equal to sine inverse, well, that would tell me that sine theta is equal to just x. And if sine is equal to just x from SOHCAHTOA, sine is opposite over hypotenuse, meaning that this side right here will be the square root of 1 minus x squared. All right. And at that point, well, that would tell me that cosine of this angle, cosine is adjacent over hypotenuse. So right away, look at that. Cosine of theta would be adjacent over hypotenuse, so square root of 1 minus x squared over 1, which is simply just 1 minus x squared square rooted. All right. And notice that I did this with the triangle being on top. It turns out that if I did the triangle on bottom, nothing really changes, nothing major. It's just where the triangle is. And let's actually make that look like it's going to go on the bottom by shifting this a little higher. There we go. So if I draw my triangle down here now, right, I start with the same exact way, saying that theta is 1 minus theta is sine inverse of x, so that sine theta is just simply x. So here's theta. This side would be x, meaning this side over here would be 1. And this side over here, by the Pythagorean theorem, is still the square root of 1 minus x squared. Even if you wanted to call this negative x, well, from the Pythagorean theorem, this part would be the square root of 1 minus negative x squared. And then negative x squared is just positive x squared, and you're left with the same exact statement. So whether we work with the triangle on top or on the bottom, either way, we end up with that identity right away. Let's look at another one. Let's say that was I. Let's say that I have something like tangent of cosine inverse of x plus 1 over 2. All right, and we want to show that this is equal to the square root of 4 minus x plus 1 squared, and all of that over x plus 1. So once again, I'm just going to start by saying, well, the inside of tangent must be an angle, so I'm going to call this entire thing theta. And if I build a right triangle, let's do that better. That's pretty good. So if I build a right triangle there, I'm going to say this is theta. And from here, it's implied that cosine theta is equal to x plus 1 over 2, right? Because theta is equal to cosine inverse, so take cosine of both sides. So from SOHCAHTOA, cosine is adjacent over hypotenuse, so the adjacent is x plus 1, the hypotenuse is 2. Meaning, by the Pythagorean theorem, that the remaining side would be the square root of 2 squared minus x plus 1 squared. In other words, the square root of 4 minus x plus 1 squared. And now, since I want tangent of theta, tangent from here would be opposite over adjacent. That's not the adjacent. Opposite over adjacent. And look at that. That's exactly what we have over here. So right away, we see that tan theta would be, in this case, well, you know what, I'll rewrite the entire thing. Well, yeah, tan theta is equal to the square root of the opposite, so 4 minus x plus 1 squared, and all of that over the adjacent, which is just simply x plus 1. All right, so we can use triangles to verify some identities as well. Now, that is the end of 5.2. And again, the idea is that whenever you're working with identities, start by choosing the side that has more stuff to do. All right, the one that looks like it has more stuff to do, and then use some of the different identities to rewrite it. All right, some of the identities that we've spoken of in the past. And if you need to include the Pythagorean identities, do so. If you need to include the reciprocal identities, you're free to use whichever you want. The point is you have to start on one side and end at the other. All right, so that is the end of 5.2.
Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. but you do have to be good at it. I am Jose Orozco. Goodbye.